The quantity we got in the last video actually has another symbol that represents it. This is called the multinomial symbol, or multinomial coefficient, I should say. And it looks very much like the binomial coefficient, except that instead of just one number on the bottom, we put the whole collection of numbers that represent how we've split up the n. So the numbers on the bottom down here all add to n, the number on the top. That's called the multinomial coefficient, because when you take a power of a multinomial instead of a binomial, you get these coefficients. We're not going to look at that any more closely. It just gives you a reason for that name, or why it was chosen. So that's the multinomial coefficient. On exams, I would certainly want you to be able to express it using the factorial. But this other notation is pretty convenient, and certainly you should feel free to use that other notation, this multinomial notation right here, except when I ask for it in the factorial form, or when you need to get a number. Now, what we're going to find out is this multinomial coefficient comes up in a very different, or what appears to be a very different context. In the previous one, we had n objects, but they fell into groups that were indistinguishable within the group, n1 of one type, n2 of another. So they were all indistinguishable in the subgroups. But in this problem, we're actually going to talk about distributing a bunch of distinct objects, no two the same, into distinct locations like boxes. So let's take an example to lead in, and we'll see how in the world it has the same sort of answer as the previous. So a math club is going to reward the top 3 officers with some books. So there's 15 different math books, let's say. I didn't say that here, but let's say there are 15 different math books that will be given to the president, secretary, treasurer, and vice president, so that 6 of them go to the president, 5 goes to the secretary, treasurer, and 4 go to the vice president. In how many different ways can the books be distributed? So, okay, I'm going to show you a way that this relates to one of those strings of different types of objects in the previous video, several of which the same, type 1, several more of which are the same, type 2, etc. And how in the world can I do that? Well, the way I'm going to do that is line up the books. So the books are book 1, book 2, through book 15. Those are different. Now, to decide how to award them, I'm going to get a permutation of 6 P's for president, 6 of these, 5 S's for secretary treasurer, 5 S's, and you got it, 4 V's for the vice president, 4 V's. So there's 15 here, and any ordering of these would tell us which books to give to the people. So if this is the ordering we end up with, the one I've got written down here, then the first 6 books would go to the president, the next 4 to the secretary treasurer, and the next 5 to the secretary treasurer, and the last 4 to the vice president. But maybe that's not the way they're going to be awarded. How many different ways we can do it is equivalent to how many ways we can permute those. The 6 P's, 5 S's, and 4 V's, because any one ordering, if we have the books already lined up, will tell us which books go to the president, etc. So there are 15 factorial, choose 6 factorial, 5 factorial, 4 factorial ways. Yeah, and that's a general principle. The general principle says the following: the number of ways to distribute n distinct objects to k distinctly labeled boxes, like box 1 through box k, such that n1, that should be an n sub 1, go to box 1, n2 go to box 2, all the way through nk to go to box k, where the n sub i's add to n is n factorial over n1 factorial, n2 factorial, etc., also known as n1 split, n split into n1, n2 through nk, different groups. Yeah, so and the proof is really not any different than what we'd have up here. I could, instead of P, S, and V, use the letters 1, or the numbers 1, and how many of these would I have? I'd have n1 of them. 2, I'd have n2 of these. Through k, I'd have nk of those. To order in a way, and how many different orderings can I have of that? That's it right there, based on the previous theorem. So there it is. Very different problems, but they have the same computation. So let's take an example of this, and it's kind of like the first problem, except now we're dealing out cards and not books. In how many ways can a deck of 52 cards be dealt to 4 players, north, east, south, and west? So that's the way you label it in bridge. You don't have to be sitting perfectly with the compass or anything, but that's the way you label it as you go around the table: north, east, south, west. So there's 4 distinct players, and which player gets which set of 13 cards does matter, and that's why we have these labeled positions. And what the theorem says, you have 52, and you're going to give 13 to one of them, 13 to another box, 13 to another one, 13 to the last box. So the answer is 52 factorial divided by 13 factorial to the 4th power. And that's all it is. Okay, good enough.